Yeah, ladies and gentlemen, also from my side, a warm welcome. We decided to do this kind of tag team approach because it's already 4 o'clock in the afternoon and we don't want you to fall into sleep. So we thought it's not a good idea to have a monologue of half an hour or something like this. So you will see some slides presented by a typical vendor of these kind of products and then followed by a typical user. And on purpose, you will also see some controversials over there. We're not one-to-one aligned in what we say on purpose because there is a difference in view when you're basically responsible to run super large plants or when you're providing technologies to half of the globe, actually. Okay, we have a pretty tough agenda, only to go through the major points. First of all, we would like to quickly show what is the Internet of Things and the needs for IP-based communication. Why do we need IP-based communication down to every field device? Then second, how do we do it today? What's the traditional digital field communication and why doesn't it come up with faster adoption rates over there? And how could IP-based connectivity to field devices could eventually look like? And we would like to finalize with a roadmap. And the green dots basically represent my subtitles, and the red ones are the ones from Dr. Krauss. Okay, IoT, what is it? It's relatively simple. Companies like ourselves and most of the vendors use embedded technology since 20 years. All our devices embed electronics and specifically microcontrollers with sophisticated computational power and memory capacity today. And now these embedded systems are combined with the methodologies of the internet, and that creates a cyber-physical system or the Internet of Things. That is actually what is happening, what is the game changer at the very moment. Our devices are not linked together with proprietary networking or whatever, but really use the internet technologies over there. And our well-thought automation pyramid that basically structured our world into 5 different layers and a hierarchical communication among these layers is going to disappear pretty soon. And we have flat networks. IRC 5 years ago already had that major theme at their conference that they were talking about a flat world and flat structures among, for example, sophisticated control systems. What does it mean? In Germany, we think a lot about what's the next generation of architectural model, and we just published the reference architecture model RAMI 4.0, which is actually a reference model that sees the automation pyramid over here and combines the other 3 dimensions, horizontal integration, along the value chain, the integration of the life cycle and the engineering system and the vertical integration in one picture. It's important to understand that we have several, I can't see the laser, anyhow, aspects at the one side, which are the different views, whether you look on your plant from a business viewpoint or from an asset viewpoint is a different, and that is what we call aspects today. It's not a hierarchy in this direction. In all the other dimensions, it's hierarchical, but here we have different, let's say, viewpoints on the same thing. This is now the reference architecture that we try to utilize, try to actually bring into some test beds, or we call them use cases, to really show that this could be the new architecture of automation system in the near future. And some people believe that this will lead to a fourth industrial revolution. That's the reason why the Germans call all these IoT, cyber-physical system, Industry 4.0, Industry 4.0, as this indicates this is going to be the fourth industrial revolution over there. You don't have to necessarily share the viewpoint that this is a revolution, but it is definitely a significant change that is going on in our world and in our industry. And then that's a slider board from Rockwell. Rockwell connects these pumps to the cloud. So what is the promise of the Internet of Things? Why do people connect a pump system to a cloud? It's not obvious to do so, but there must be some business reasons, some benefits to do so. And I would like to go through 8 of the points that I have collected throughout the last months, people telling me what they believe is one of the benefits IoT could bring to process industry, to manufacturing industry. First one, this is the big thing in Germany, additive manufacturing. The Germans believe that they can onshore employment that they lost to the emerging markets and parts of the world simply because of costs, if they are able to actually produce individualized products at the prices of a mass-produced article over there. That's called additive manufacturing, and that is really driving people forward in Germany, that they believe if they can individualize their product offering and offer a product tailored for yourself, but on the price of a mass production, that this could be very interesting. And they believe they can basically come a step forward by utilizing the IoT. Same thing with predictive maintenance. Well, if you look inside the reality, most of the stuff that we do in regards of maintenance today is corrective. We're not even at preventive, not talking about condition-based, and now we're jumping over to predictive. It's maybe a long way to go, but without IoT technologies, predictive maintenance is definitely not feasible. Augmented reality is something that we already use pretty intensively by combining sensor signals with cut data to improve the quality of the sensor signal. This is typically augmented reality. It's not necessarily that you use Google Glasses or stuff like this. Even in a sensor, you can combine cut data and measurement signals to improve your measurement quality over there. That's practically the same like in the next soft sensing does combine this in real time. Next is plug and produce. That is something actually that we promised to our end customers 15 years ago when we introduced the Feedbus technology. You plug in a device, you exchange it, and all the parameters will be inherited from the major system, and it's even able to do this over a release change of the devices over there. We have to admit that we can't do it today. It's still a nightmare to do an exchange of products in a digital communication network as of today. But we believe with the IoT, with the technologies available over there, we can come much closer to this vision of plug and produce. Condition-based maintenance, I managed this already. Before we do predictive maintenance, there's a lot to do in regards of condition-based maintenance where we use also the internet technologies. Modular manufacturing instead of really scaling up our system, which is really a hard time if you have a manufacturing or process plant that is designed to meet 100% output and you would like to enlarge this by 20%. Scaling up is a nightmare for most of the producers. If you could do this by numbering up, simply modularizing your production and putting additional modules to it, this could be definitely, especially in the pharmaceutical industry, a large winning point if using IoT technologies. And then cloud-based per-use distributed control. If everything is IP communication from the field, your distributed control could be anywhere, even in the cloud, and you not necessarily need to buy hardware or stuff like this. You simply pay what you use over there. Now, we might be many years away from this, but again, without Internet of Things technologies, this is not feasible at all.
Okay, good afternoon also from my side. So also I would like respectively give you a view of what IoT means to us. And here, this is not related to automation or technology in particular. So this is coming out of a joint effort we have done BASF-wide together with our IoT department mainly to develop a view of BASF on IoT. And also I would like briefly to take the chance to make a little personal note because in several sessions in this conference, I have heard rather skeptical comments about the role of IT, the capabilities to run highly available systems, on their integration skills, also on their personal skills. And so here I would like to make the remark that here I was really confident and that it really was fun to make this together. And I found people who were really eager to understand what are the needs also of process automation. And so I would like to encourage you to also search for those people in your organization. Okay, so IoT for us, in a very general framework, is about architecturally enabling services by equipping objects with sensors and actuators so that they can exchange information among each other. And for us, a decisive factor is that this is IP-based and not based on any other technology at this point. And by this, a thing is then an object which can be identified and managed and integrated in communication networks, so the cyber-physical system. So in the sense, this was also for us the manifestation of what means smartness, that the systems have a kind of a self-awareness, so that they can manage their sensors themselves, that they have an idea of what are their capabilities, their services, and what is their environment like in terms of a simulation type approach. Still very general, so what can we conduct so here as possible benefits for process industry in general? The first aspect is to improve customer satisfaction. A lot of this goes into supply chain aspects, so that customers know what they will be delivered and when, and that, for example, at the time of ordering a product, they will also see when it will become available for delivery, and that they can also have options and interactively act with the system, for example, to change certain parameters and see the influence of the delivery time. The second would be creating a top-line growth based on new business models, so enriching the products by services coming, for example, also from big data and analytics out of data of the CPSs. The third one, the increased efficiency, that's probably the one in automation we think most about what we can do, so improving the monitoring and the integration of manufacturing facilities of the equipment. So here plug and produce is a very important buzzword around this, and the interplay of augmented reality to optimize the use of the scarce resources we have today. And the fourth point, the safety improvements. This is also a field we see very promising for IoT technologies. This is not related to the process safety, but to aspects of like occupational, transport, distribution safety. And for example, one use case out of this domain would be more equipping people with sensors, monitoring their location, their acceleration, their temperature, their hydro status, etc. As I said, for us, it's mainly an architectural question. So all these benefits you could achieve either without IoT technology or with IoT technology. And therefore also, here I come to the conclusion that both a traditional operation technology and IoT will coexist for an unforeseeable future. We see mainly the dividing line between both through the native connection directly via IP and via different layers, and the smartness of the devices. So here we have on the left side our traditional operation technology, where devices are connected either via gateways, non-IP protocols, or IP protocols to control systems, to MES systems, and data are aggregated further up. While on an IoT side here, equipment like this truck are natively connected via IP directly to a managing cloud. So cloud which is gathering the data, and on the other hand, which is managing the devices. And also here, as a remark, you do not see, for example, a valve. So it's not the intent to have here process critical equipment on this side, but this is about the equipment which can safely and securely realize use cases on this level. A border case here, which we still count into the traditional operation technology, would be a further modularization of automation. And another remark is that things can be, if they have multiple communication channels, also be part of both worlds. So they can be embedded into the traditional operation technology with tasks like opening valves, measuring process critical temperatures, and on the other hand, they can report directly, for example, on their condition. Our approach to this, how we will drive this 2016 and further, is that we are about to implement a lab, because we believe that we cannot engineer these solutions with sufficient maturity from the startup, so we need to experiment in a certain sense with them to learn about the technology, the cybersecurity features, the functionality, also what are suitable IoT cloud platforms for this, and to have a knowledge transfer later then into the actual projects. And this all is done by a cross-functional team where we bring together experts with an IT and OT background, with cybersecurity skills, and network also with academic institutions and the solution providers.
Thank you. Okay, good. Coming to the state of the art. of field instrumentation today, as you can see, we have a mixed architecture. We have a coexistence of analog technologies, sometimes utilizing the HART protocol. Most of the analog devices in the field use the HART protocol just one time when they're installed. So you do the parameter setting and then you forget it. We are talking about what we call stranded HART data. So they're residing in the device and that's it. The remote terminal units, or remote I/O systems, how we call them, are essentially the same. That's just the backbone structure of the CPU or the DCS system behind. But towards the field device, it's the same, 4 to 20 milliamps. Most of the remote I/O systems or RTUs support HART today, but the question is it really utilized in the field? And then in parallel, we have Foundation Field Bus or Profibus PA as the only true digital communication system which are currently existing in the markets. And the Field Bus technology can provide an entire infrastructure through the different zoning or classes or divisions regarding the explosion hazardous area, which is always in the chemical and hydrochemical industries an absolute must. There is no way of basically excluding this from your requirements. You have to consider what to do with the hazardous areas over there. But this is really what we install today when we are considering a Field Bus Foundation or a Profibus PA project. We can offer a lot of stuff which, for example, advanced diagnostics would allow to go forward in regards of condition-based maintenance. There's a lot of software support in diagnostics, but also for commissioning the systems over there. You can save really considerable time in the setup, and the devices on the field level, like these field barriers, or you would call them electronic junction box with hazardous area protection included, is really mature now. It's the third generation of products that we're rolling out to the market. And as you can see, most of the users will clearly state that the physical layer of a field bus system today is ultimately robust, much more robust than a 4 to 20 milliamp analog signaling over there. It doesn't need any kind of accuracy trimming or whatever. It's really a stable network today. And still, it's the case that users do not change over. The adoption rate is slow, and some of the users do not change over at all. This statistic is a little different from what Mr. Forbes has shown us, but it's our statistics. This is what we sell. So 70% of our IOs is really HART technology. Again, analog and HART, hard to distinguish simply because nobody knows how much of the HART devices really use the HART protocol constantly. And 20%, that is what we sell as of today into the field bus technology, and 10% is really purely analog, even without HART technology over there. So this is what we sell today. That's not accumulated. As we speak, this is the basically spread of the different technologies over there. So field bus has not even gained the majority in regards of greenfield installations, not talking about brownfield, not talking about retrofits over there.
Okay, I have only one slide here on examples why we are, as end customers, maybe not embracing field bus technologies to an extent manufacturers would like to have it. And for fairness reasons, I have chosen one example with Profibus PA and one with Foundation Field Bus. So on one of our Foundation Field Bus installations, we experienced really extended problems over a long time till they were really finally fixed. And the problem there was that temporary distortions were caused by a partially erroneous installation. So, and if you're talking like thousands of devices and some shields are not perfect, then you might have some electromagnetic interference coming from frequency converters. It's not necessarily perfect. Also, what was coming into play here is that we had larger problems, especially when exchanging devices. And the problem behind this was that the redundancy concept had a time-dependent factor in it. So switching from master to slave took a certain time, and if you are creating disturbances on the bus which are on a similar frequency, so you disturb the master, and before the switchover is finalized, it's already back on, you will end up with two masters. And so this caused certain problems here, especially, as I said, when replacing field devices and you have the unisolated ends and you are short-circuiting it with a high frequency. The second example is from a Profibus DP and PA installation. So this is later in time, so we are already quite interested in this topic and conscious. So we had done high efforts, especially for the potential equalization across the plant, because we wanted to allow for the both-sided grounding as it was requested from the documentation. Nevertheless, the quality tests after installation revealed several weak points in the cable installation, in the real realization of the grounding, and maybe also the surprising fact for us was that the PA, which we were more scared of, was executed in a better way than the DP, and we had to do more rework in terms of interferences with power supplies, etc. So the conclusion we have drawn from this is that if we want to have really a perfectly running field bus installation, we have to create a kind of lab-type environment to really have kind of perfect installations. But even if you undergo all these efforts, you're running into high demands concerning the explosion protection, because if you have far extended plants with both sides grounded, you need to make sure that you have equal potential across the whole plant. So this means a high effort to ensure the availability of the chemical operations in the end, and you have undergone all this in the end for like 30 kilobit of data transfer rates, and you still have problems with the device integration, so with different versions of field devices. And so then you might ask the questions if this is really worth all the trouble which it is giving you.
Yeah, shame on us as vendors that even 15 years after Fieldbus introduction to the market, we still run into problems with installation issues, grounding, so really the field work over there. Maybe in this case you have chosen the wrong vendor, I don't know. But anyhow, there is a NAMO recommendation. You might know the NAMO, the Normenausschuss für Mess- und Regensehen. So it's a standardization committee for measurement and control in the chemical industry of Germany that was funded after the war. So it's really a long-dating history that they have in really looking in process control. And they are issuing recommendations, so-called NAMO-Empfehlungen, NE. And the number 74 was on field bus requirements. So the question, what you need to do to achieve an appropriate installation over there. And this is still valid today. There is an extension and a renewal of this, but in essence, it is still okay. So if you want to do something in regards of digital communication, it's pretty smart to look in this and to understand what are the requirements, because they're not changing. The requirements are coming from the nature of hazardous industries over there, and they're not changing when you are changing a technology over there. So we took this as an advice to actually come to a better solution for digital communication over there. For example, here they clearly state that application explosive atmosphere is imperative. So you can't basically neglect it by saying, well, we're handling this case a little later over there. You have to consider this requirement from the very beginning. Same on the cable lengths. They clearly differentiate into what we would call a spur, which is really the last meters to the field device, where they require up to 200 meters, and the trunk, which connects several of these field barriers or field switches, and the trunk length is required to be something like 1,000 meters to really also stretch into largely expanded fields over there. And very important, the last sentence, they require two-wire cable for data and power. They don't like connectors at the very end. And if you have basically wired 1,000 meters through a chemical plant with hundreds of cable plugs and stuff like this, you know why they don't like connectors over there. It is imperative as well that this has to be on two wires, that you can put them on a terminal rather to put them into a plug. That's the same also in regards of reliability. A connector system is not as reliability as a terminal. That is an experience that we all had to do throughout the last 20 years. So we took all these basic ideas and a thought about what can we do to actually create a feasibility study. How could a physical layer that is able to talk IP, that can handle IP protocols, how should this look like? It has to actually meet the requirements of the field bus structures from the chemical industry, from the Namur, and at the same time it has to be integral part of an Ethernet communication. So it has to be able to talk to the Ethernet data link. So you can see on the very top, it's a standard Ethernet that combines several of the standard equipments, like for example, a standard PC, which runs a certain software, and you have a wireless LAN router, and you have a switch, and that switch then converts the standard Ethernet into the two-wire physical layer that we have over there, and that actually provides the capability to a trunk of up to 1,000 meters that is wired in the hazardous area in what we call increased safety, so EXE, or there is even a new technology available to do this intrinsically safe with increased power, that's called DART, that can provide up to 50 watts on such a line in intrinsic safety. And then it goes into a field switch, just a switching topology like you normally use it when we wire such Ethernet structures. And from that onwards, it connects to the field devices, and the switch as such provides two-wire intrinsically safe spurs, and each spur can cover a length of 200 meters. So we try to cope as exactly as possible with the requirements of the Namur recommendation. When we built up this demonstrator with a number of other companies giving us advice and also hints how to do this over there. So all in all, 20 companies were participating at that, let's say, open collaboration on what we called at that time advanced physical layer. And we were actually showing a demonstrator of this first time at the Hanover Fair 2015, so almost exactly a year ago. And this demonstrator then was basically connected to several multi-vendor devices over there that basically did the exercise to embed a small Ethernet kernel in their devices and a small APL physical layer adoption over there that was provided by us. Relatively nice design, so it's not really a three-dimensional prototyping stuff, but really something that was much closer to realization than just a feasibility study. And then we also included software and stacks inside of these different devices, and that allowed us to actually come up with a system that actually looked relatively professional. You can see at the one side the switch that turns the standard Ethernet into the two-wire Ethernet, and then this links into the field switch that basically connects to the field devices over there. And the performance of this network was it could work with 30 volts and half an amp, so relatively nice power to really power up something like 40, 50 devices. And the trunk length was up to 1,000 meters, intrinsically safe spurs up to 200 meters. The speed, we were able to show that we can easily achieve 10 megabits full duplex over there. It is still an ongoing debate whether this is enough, because if we, for example, put highly sophisticated softwares like OPC-UA in the device, we might require a higher bandwidth over there, but that somehow violates the intrinsic safety conditions because higher bandwidth means higher power. So it's a trade-off that we have to find. And there's an option to increase power with DART. It's a switch network topology. So all in all, already a pretty feasible concept over there. And what we have shown over there were 2 out of the 8 different test beds or use cases that I've shown you. One is the plug and produce, really showing that you can plug in a new device, and as we put all the necessary information to handle and integrate this device into the device, it could automatically upload and configure itself inside the engineering system, which was a completely new scenario over there, because at the very moment, you have to download this from some web pages somewhere over there. It's not residing in the device because the bandwidth of ordinary field bus systems with 31.25 kilovolts is simply too small to actually allow such a highly sophisticated data stream. With that 10 megabits, that was no issue to show that in fractions of a second, you can upload all the necessary information and do an automatic reintegration of a device inside such an asset management system, for example. That's not completely new. We promised this plug and play 10 years ago when we introduced FieldBus, but only now we can see with the IoT, with these capabilities, of IP communication down to the field devices, we would be able to do so. And that leads directly into condition-based maintenance, because now you have the capability for no money to get the health status of all your assets inside your system, telling you when to change the devices in a planned shutdown rather than to wait for an unplanned shutdown, which is much more costly and basically tears down your availability of the plant. All of the devices had an embedded web browser, so for the first pass investigation of the devices, not even an engineering software would be required. It's just a standard browser allowing you to look inside. So that's exactly what you do when you utilize internet technologies in the Internet of Things. You use standard equipment, a standard browser allowing you to dive deeply in the devices. Everybody knows this from his little camera he hooks to the internet at home over there. Same methodology, same issue, same cost. It's really nice. But on the other hand, you can also use it to integrate it into a more sophisticated system. In this case, it's Packer, but it could be any other asset management system that supports the FDI stacks and the FDI device packages over there, which have been newly released recently. Now, this is something that wraps around the devices and is, if you wish, a digital twin of what we do over there. And this is really a seamless integration. But this requires high bandwidth to the device. It doesn't work with the standard existing analog or field bus technologies over there. One interesting slide I would like to share with you was from Mr. Schlichtmann, also from BASF. He was giving a presentation at the NAMUR, and he was focusing very much on plant asset management. And this number is really cool because I always state that it's like this, but now I have it in writing. 70% of what maintenance people do is corrective action. So something goes wrong, they go into the plant, they change it over there. And then another 24 is just preventive. Just because, you know, well, normally it takes a year and then the device gets older, is aging, so I better exchange it by half a year. That's what they do when they do preventive maintenance. And only 6% is condition-based and predictive maintenance. So this new approach virtually doesn't exist in our industry today over there. We need to radically improve this because we are wasting a lot of money and we are taking a lot of unplanned shutdowns into account if we just do corrective actions over there. Everybody knows this. And Mr. Schlichtmann basically said, well, then we try to elaborate something by doing a big data analysis, by simply pulling all data on a part of the plant together to really do a modeling of the health status of the entire plant. And we found out it takes us weeks until we get a complete set of data. 60% of the effort is just a waste of time simply because we need to, first of all, clarify the access to the data. Then we have to clarify the data themselves. We have to include domain knowledge. So all in all, this adds up to 60%. And then only the remaining 40% is really about analysis and modeling and stuff like this. And therefore, he clearly formulates, if we want to go farther down the line with predictive maintenance or condition maintenance, then data must be available like power from an AC outlet. Of course, in his presentation, he used a German outlet, so I changed this to make it understandable for you guys as well. And that's it. Data all of a sudden is more than just a signal coming from a sensor, like a pressure sensor or transmitter or something like this. Data requires an infrastructure, and an IP-based communication into a field device is an infrastructure.
And a lot of the 60% was also simply extracting the data because it turned out that today's PIM systems, etc., are also not really suitable if you want to do a mass export. So this was also an interesting experience for us at that point. Okay, concerning the physical requirements, the future requirements and characteristics for a field bus, I can join most points. IP-based, intrinsically safe communication on 2 wires to make it also robust against index exchanges. And well, I have written here more than 100 megabit. So this is a kind of a number you never know what happens. So maybe you also get along with 10 megabit, but it's also important to keep manufacturers motivated.
Busy.
Yeah, in the end, to have an easy installation basis for the realization of the use cases in the framework of digitalization we're all talking about. Second, the robustness is an important aspect for us, so the error correctingness. This should not be only done by repetition of the signal, but there are more sophisticated technologies out there. I have, as an example here, ADSL-type error preventions and corrections, and all the modern communication technologies, be it 5G or vectoring technologies, are really about extracting a lot of information quickly out of basically garbage signals. And so if we reduce this a little bit so that we have, of course, higher quality signals, I think it should be possible to extract more information out of this with a high robustness. And the third point, because we had this experience now at several plants, no grounding at both ends by specification, so no hard grounding due to the equalization effects. Maybe it could be a capacitive grounding at that side to facilitate the explosion protections within the plant and to achieve equality really by the specification. So we do not want to simply do it single-sided and in the end test that it's still okay, because maybe it's not okay if you add some more frequency converters or at different locations within the plant, so that this is really by specification. One thing I would like to add there is that so far we have talked about the transport layer, but also what's important to keep in mind is the device integration. And also here I've stolen some or copied some slides from a NAMO presentation, which shows we need a street between the DCS and the field devices. And here it's important to have one uniformly specified physical layer for our devices. And additionally, how do we come from one side to the other is that our communication participants should support at least 2 protocols specified for process industries to also make this more robust against different kinds of installation to make it more interchangeable. The idea here would be to take the 2 widest spreads protocol, which would be Profinet IO and Ethernet IP. So this would also give this kind of integration a very multinational approach, where Profinet is more wider spread within Europe and Ethernet IP in, for example, North America. And then there are other aspects like backward compatibility, scalability, and modularization concepts, and easy to apply for end users. And what this really means, or in more detail, easy to apply for end users, this we are currently specifying in a document. There are aspects of the lifecycle management, how long devices should be operable by specification, what it means in terms of security, exchanging field devices, replacing field devices with newer versions, etc.
Okay, so where are we today with the Advanced Physical Layer project? The group that started this feasibility and was participating at the demonstration in the Hanover Fair actually is still sitting together, and there are still some questions in regards of requirements. There is obviously the wish or the requirement for a higher bandwidth. 100 megabits is something people actually would like to have, although current data models and current devices actually do not require it. But that's like usual, if you have the capability to go for 100 megabit, why should you start with 10 megabits? Because it's sure somehow you will need the 100 megabits. When you, for example, think about including a manual inside the device, and that manual maybe includes even videos, all of a sudden you have a demand for higher bandwidth over there. So there are, of course, a lot of reasonable ideas why 100 megabit could be required over there, but on the other hand, it's a trade-off with the power, it's a trade-off with intrinsic safety, it's a trade-off with complexity, and it's nice to think about ADSL technologies, but ADSL chips are done for communication purposes that sell in the 100 millions per pieces per year. Automation technology sells in the millions per year, so we also have to take economical figures into account. It's nice to dream about such a technology, but if our devices would then be loaded with another $250 extra just for the communication chip because we are not able to provide 100 millions of quantities over there, that's different. So like usual, automation people are pretty smart in stealing technologies from other areas, from other domains, but we failed miserably in finding a chipset that would be suitable for our kind of requirements. It simply doesn't work combining these standard available chips with a technology that goes into the hazardous area and needs to be intrinsically safe over there. This is currently an open issue. We are still debating in that group, and there's still talks going on and also severe technical laboratory projects going on to find out how feasible is it to increase the speed to 100 megabits? Will it be necessary to make an intermediate step of 10 megabits first, and then once we get smarter over the years and maybe other technologies are on the market, we could change over backwards compatible to 100 megabit. That happened with the standard Ethernet the same way. So this discussion is not yet finalized. We hope that we are able to basically finalize this around the Hannover Fair, because we are sitting together with these people almost daily to actually see some more progress over there. And we have a lot of players, super large companies, but also small companies over there. It's not so easy to do this in a full consensus over an industry over there. But all our plants are multi-vendor plants, so we can't come up with proprietary solutions. So what do we do in between? BASF also asked us, what do we do with the devices that are installed? How can we actually make data available, like our power from an AC outlet over there? And one possibility is just under consideration also inside BASF is the wireless HART technology, which is a simple mesh network. You can plug in these kind of bullets or adapters into a device and turn a standard HART device into a wireless device and collect the stranded HART data. So over there, that's at least a doable alternative plan to develop an infrastructure for this kind of data over there. And it works nicely, actually. There is a lot of support available over there, even software that shows you the wave propagation, so you're not running into problems because you have a lot of steel inside your plants and the wave propagation isn't sufficient to really create the mesh network over there. You can simulate this and basically find out where to set the necessary gateways and hotspots to do an appropriate coverage of the entire area over there. And people do use it, and they use it in the standard way by really plugging such a connector or gateway or whatever you call it into the device. But some of them even combine several of them to transmit several systems. And you see there's a lot of steel around, and still that is doable. A gateway or hotspot looks like a standard hotspot actually, and provides the wireless HART infrastructure over there. Some people say, well, this is all nice, but it's not really for the rugged, for the rough environment over there. Not true. This is how it looks like when it's used heavily in the chemical industry and still working over there. So this is really a technology that you can use in between, although most of our customers think that this is more niche character. You have it for mobile equipment and stuff like this, where you don't want to run cables, you use the wireless. And until we don't have a IP-based communication to the field device, it might also serve as a standard infrastructure for data over there. So there's a migration path forward, because from the time frame, you can see it might take a little longer until we have an advanced physical layer available. Our expectation is if we manage to have a consensus in the industry on the final specification of this year, we would be able to release something in the market not earlier than 2019. That's still 3 years to go over there. And in the internet world, 3 years are actually 12 years. So that's a tremendous time that we need. So we need to actually provide solutions also in between.
Okay, and I also like to pick up this idea on my final slide. So the idea of parallel communication channels is basically hovering around since the introduction of Industry 4.0. And on what this means in more detail, I'm also currently working with two gentlemen in the audience, and from one I've stolen the picture, so shame on me. Yeah, so an approach might be really necessary to have a parallel wireless infrastructure in the plant as an intermediate solution, and especially as a retrofit solution. Because we have all these long life cycles for the whole asset equipment, and this will not be exchanged for the purposes of communication. And wireless technologies, especially also if you use maybe cheaper sensors which do not fulfill the full process requirements, but are enough, for example, for condition monitoring, you can equip devices to a certain extent to make them alike a cyber-physical system, so to retrofit them with communication capabilities and with sensors to make them cyber-physical systems. using this as wireless, we especially see benefit in overcoming the constraints we see from current field bus technologies in terms of complexity and bandwidth. And we see this as an add-on philosophy instead of a replacement strategy. So you could run, even with analog signals, all over the robust 4 to 20 milliamp signal, and additionally have a high bandwidth for additional information which are not critical for the process, which channel which also can stop sometime because you need this information then primarily for condition monitoring. Nevertheless, this is an additional effort to have such an extra communication platform, communication channel. And so for the very long time view, of course, the convergence of the wire is preferred. So to merge this again, the highly process critical communication and also the add-on on a common wire would be the preferred solution in the long term. Okay, so thank you very much.
Yeah, also from my side, only a closing statement. As I'm doing some of these Industry 4.0 and Internet of Things presentations quite frequently throughout the last 2 years, it's really remarkable that everyone talks about the benefits of Industry 4.0, especially on the very top. And if you go down the line, people actually exclude devices from the Internet of Things. So the things are all of a sudden not part of the Internet of Things anymore because, no, they are out of a protected area. It's my field device, and I am, as a measurement and control engineer, looking for this. And this is not an integral part of the Internet technology and shouldn't be because it takes care about safety and whatever issue over there. I simply don't think that this is the right track, that this is the right way we should go. If we really believe that there are benefits in the Internet of Things, in the IoT technology, then we need to include all the assets, all the things to that Internet of Things. Otherwise, we're still running analog signals, we're still running signals into the next level of control where the data got stranded because a measurement signal is not data. We have to change our sensors from giving us signals to giving us data, and therefore they have to be an integral part of the Internet of Things, and that requires an IP-based communication down to the field. Thank you.